today, given by Professor Dr. Christian Mayr. I'm very happy to announce this workshop or this seminar as a part of the. I have some echo here.
Let's not call it a beef, but what I have with neuromorphic is they tend to focus very much on the edge. This thing I've got up here in my brain has 10 to the 15, 10 to 60 parameters approximately. So if that is not cloud scale, I don't know what is. So it's a cop-out saying, yes, we just go for the ultimate edge, and where the analog signals or the sensors are, you can actually get quite a bit of stuff also from the brain for the cloud stuff. But I mean, there's still an echo. Wait a sec, but no. There are VSI systems and neuromicroelectronics. I didn't come up with that name. That was my predecessor, René Schöffni. We were endowed chair by Siemens Infineon mid of the 90s, building the first wave of AI hardware. And then we kind of got sidetracked into the neuromorphics, doing neuromorphic image sensors. Then, of course, in the precursors to the brain project with the Heidelberg guys and the Facets BrainScales project, we co-built the wafer with them. So that's why we are chair of neuromicroelectronics, which actually seems to be a new word, right? It's not really neuromorphic. It's not really bioelectronics, but it somehow even captures our true direction, right? That we do these implants and we do the bioinspiration. So anyways, we're about 40, 45 people. Of course, very much coming from circuit perspective, analog digital designers. But then, of course, basically we've very much moved up in the stack, building our complete software stack as well. And as I said, we've got a line of neural implants, so that also means I actually have medical people on my payroll. And of course, we all get excited about chips, but the general public not. So you have to have the chips moving something. So we do quite a bit of robotics as well. Our biotope spin-offs, Ray6, that's the oldest one, 2009. The channel partner Global Foundries, they do a lot of basically chips as a service. So you come to them with the idea and they do the entire chip system or just parts of it. And they have a lot of knowledge on this, especially adaptive body biasing. I'm going to come back actually to the startups later. Then there's Silicon Valley, which is doing communication links, because we learned so much about doing communication links for the wafer in Heidelberg that we spun off a separate company for that. And they actually also contributed, of course, to the Spinnaker 2 design, the link architecture. Then we did a short spill doing Bitcoin mining. Then there is now, of course, Spinnaker Systems commercializing Spinnaker. And Silicon Valley is kind of a working title for the neural implant startup, which is going to happen next year. So that's about 250, 300 people in the startups. Direction. Right. So I would say our uniqueness is that we focus very much on the system on chip, which actually not a lot of academic groups are tackling at this level, because it takes a large chair, it takes a lot of work division. Usually it's this one PhD, one chip basically thing. Actually here, my people, it's more like one PhD doing single accelerator or doing a single communication link. So it's rather the IP blocks on the chip. So usually, so we do all of these things that other chairs do, right? Sensor conversion, AD converters, whatnot. Communication architectures, adaptive body biasing, etc. But we always subsume them in the system on chip, which actually also means that we need to do them way more reliably, right? Again, the slight beef I have with academia there is they for example, they build an AD converter and they build it very much to the edge that 1 out of 10 works. But that one gives you super energy efficiency. And then they measure that one, they publish an ISSCC, and of course it's not effectively designed. It never will see the light of day in private industry, but they have this very cool kind of KPIs on that thing, right? And we usually take a notch back, because for us, of course, the whole system has to work reliably. So we can't do the individual building blocks at that level. Which always makes it actually quite hard to publish this stuff, right? There is not a lot in IEEE journals. They can really publish at the system chip level. Usually you have to have a single building block. We do a lot of tape outs, right? Even before Spinnaker, our chips were used as kind of research tools for other groups. So that's what we also pride ourselves on, that we actually do this at quite a high, again, reliability or maturity level, right? You don't need 3 or 5 PhDs kind of fine-tuning biases. You just plug it in, it works. And especially for Spinnaker, we do this across many orders of magnitude, actually 14, right? In Spinnaker, there is single chips single transistors we touched, really in the power management, in the link structures. These are analog optimized, really classic design transistors, but then of course the whole system is 70K chips, 14 to the 10th transistors in there. So yes, that's kind of a whole scale recovery. Yes, and of course we embedded in silicon Saxony, so we take advantage of a lot of that, right? In terms of packaging, in terms of yeah, the whole supply chain basically being close to global foundries, being able to do short wafers, etc. By the way, who gets the reference? Okay, at least some of you, right? That's Monty Python. No one expects the Spanish Inquisition. This is still from a talk I gave in Manchester when we sent Steve Ferber off to retirement. And that was somehow between stand-up comedy, a little bit of science history, and yeah, just putting in Monty Python jokes in there. Okay, so that's going to be the structure. So let's talk about Wi-Fi inspiration first. Then we're going to talk about Spinnaker 2 and also edge systems, and then algorithms and use cases. So just to explain before I start the video. So this is from the guys in Jülich, the main video. This is basically zooming into a brain. And then this is a video from the Heidelberg guys. I never did one for a Spinnaker wafer. So that's depicting the wafer, the layout. And now we basically zoom in on both sides. So the point being, right, the wafer started 300 millimeter, the brain started whatever, 10, 15 centimeters, kind of roughly the same dimension. Then you zoom in. Now you get the millimeter to micrometer scale. You're starting to recognize cells in a micrometer. You're starting to recognize at least power supply up in the right corner for the wafer. So that's already inside a single chip, inside a single reticle. And now we keep zooming basically. So then you are at the signage, right? It's a couple of microns across, actually below a micron. Now you have the vesicles. So now you're at this double-digit nanometer scale. Same thing up here. So we're basically ending up kind of at the same scale on both sides. And that's not even the latest technology, right? That wafer was 180 nanometer. So that's of course not this usual 2-3 nanometer process today. The point being, we basically in semiconductor at a scale that can actually mimic the whole brain. That also occurs why AI is coming up these days. A lot of people, especially in Germany, if I look up the German Wikipedia page for AI, it says AI is a subtopic of computer science, period. If you look up the AI entry in the English Wikipedia, it says it's a crossover topic between biology, algorithms, and hardware, right? So the Americans take a lot wider view of the English-speaking world than the Germans. So of course, AI would never happen if we didn't have this processing power, right? The storage power, etc. So that's really, I mean, the algorithms, they kind of now are advancing, but it started out this whole craze with basically algorithms from the 80s, right? Back 10, 15 years ago. So what really advanced AI, this first wave of superhuman results for ResNet or whatnot, was essentially the hardware getting better, right? You had more data to train on and you had the compute speed to train it on. So that's my motivation why we really go brain scale, because in essence we can. There is a technology that we have in our graph that really goes to the same scales. Now, a bit more in detail, what am I shooting at? So my background is from this kind of regular neuromorphic stuff. So really building synapses and neurons in CMOS, playing around with membristors and whatnot. But I've kind of moved up in the stack a bit. So I don't try to copy every last bit from biology. And I don't try to also emulate everything in hardware. So I'm rather going for these general principles in the brain that really scale also to the cloud scale, right? I don't need 2 different types of long-term plasticity in my synapse and 3 different types of short-term plasticity, right? Then down to what we can really, because the trouble also with neuromorphic engineering is they usually put in all these effects because they're all cool, and then they cram whatever, a chip or a wafer full of them, and then they expect emergent behavior. And of course, that's what the machine learning guys basically taught us. At those scales, you also need a top-down flow. You can't just expect cramming everything together and then something wondrous happens. So that's my problem with putting in too much biological effects, which we A, don't really know what they do, and B, we can't really train them to do something sensible. I mean, biology probably does that. Biology is not stupid, for some reason, but at the moment we simply don't have the training algorithms to make sense of this huge, basically dynamic space of behavior and parameters. So I'm focusing on general principles. One general principle is illustrated here. It's basically sparsity. So you get, even in those 4-layer cells in the retina, you get 100-to-1 compression, and then of course this event coding in the ganglion cells. So meaning you do a second-order derivative pretty much of the input image. That's just in space. And then you also do that in time. So you've got space-time receptive fields in here. And then, so that's a 100-to-1 compression. So that's the sensory areas. And then if you move up across the memory areas associated with cortex, you're going to 10 to the minus 5. So you're going very, very sparse. So the brain, in my view, is a huge collection of latent resources that are indeed powered down. And then you only ever activate them when you need them. Actually, neurons are better at power down. They've got a better subthreshold slope in the ion channels than our transistors. So neurons are really optimized for essentially zero leakage. When you don't need them, they don't burn power. And then you activate them only in very specific cases. So biology is very good at doing focused information processing. Essentially, for each new problem in your brain, you are basically generating some dynamic topology that's not the same as the static topology. You can see that even petri dishes of neurons, where the information flows through, is not exactly the same as what you can see microscopically in the connections, right? So you are essentially, for each problem, you're defining kind of an information highway through the brain. And really then only activating the stuff that's along that highway. So apart from sparsity, next thing that's interesting for supercomputing is, of course, asynchronity. So asynchronity means if you can't have, so the brain is very good at running all these 80 billion neurons in parallel. And the only way you can do an 80 billion neuron parallelism is basically by going asynchronous. If you have wait cycles in there, like regular supercomputing, where one process waits for another, then basically you couldn't just utilize that much parallelism, right? There would be no point in distributing the process so much. So if you can do something asynchronous, right, then you get strong scaling, essentially, what the supercomputing guys tell you. So throw double the number of processing elements at a problem, and you execute it in half the time, which usually, again, does not happen in supercomputing. Usually, supercomputing is slower than that. So that's asynchronity. Along with that goes kind of hierarchically distributed algorithms, right? So in the end, there is this buzzword of von Neumann bottlenecks. A von Neumann bottleneck is basically, right, you've got your memory, you've got your processing, and you've got some kind of communication in between, and that is, of course, somewhat limited. So if you have to shuffle around a lot of data, get it to the processing, write it back in memory, that's going to get slower. And of course, if you do this distributed, right, local memory only access, or local processing only access the local memory, then you're actually a lot faster because you don't need to go through such a long distance to the memory over here, for example. So in essence, that's of course the ultimate then in neuromorphic is the synapse, right? You've got the memory exactly identical with the processing in a sense. But I'm going to tell you in Spinnaker, even this 10 billion for parallelism goes already a long way to removing the von Neumann bottleneck. Actually, even GPUs these days, right? They're distributed systems. The only trouble you have with GPUs is that the machine learning guys actually use them in the wrong way. Because the machine learning guys assume that the whole compute is one big contiguous compute space, the whole memory is one big memory space, and they assume infinite bandwidth in between. So they are not using, I mean, multiple racks GPUs are a distributed system, but the algorithms they are mapping on that assume basically a virtual one single von Neumann machine, right? And that's what slows machine learning down. Because you just in a physical system, you don't have infinite bandwidth between that memory resource over here and the processing over there, right? They just don't respect those physical limits. So that's also what I'm looking at when I design machines, right? That we really look at the physical constraints of the compute and try to design the algorithms along that. So all of that basically scales across multiple orders of magnitude. By the way, the last one I didn't mention, so I'm quite interested also in recurrency at the network level or dynamic computing. At the single neuron level, this is a leaky integrated fine neuron, right, that integrates across time. Most of the times, you actually don't need that we found, but some kind of recurrency. For example, this recently loop with the transformers or just RNN structures, because the dynamic computation actually lets you work asynchronously. The two are interlinked. because asynchronously means some information doesn't come at an exact point in time. Let's say gets sent off over here in the machine or in a larger system, received over here, and that receiving still needs to kind of make sense of that information. And it's not, again, there will be multiple delays or whatnot, variable delays along the way, so you can't really predict when that information will arrive here. So what you need is some kind of recurrency, some kind of integration across time, so that that information that kind of flows from here to here can be integrated as it comes in, right? This machine doesn't need to wait for that information, right? Otherwise, it would have idle times again. So that machine just carries on its computation. At some point, it gets sent some information from over here, and it can just integrate it in its own kind of information process and as it comes in. And that's where dynamic computation, where recurrency comes in. So you need some kind of integrator, some kind of memory in your processing. Okay, so let's go for the hardware. Spinnaker 2 mostly. So Spinnaker 2, 10 million ARM M4F cores in 22 FTSI, so local global foundries Dresden, each with dynamic power management. So basically, meaning that the processing elements are energy or compute load adaptive. Could be spikes coming in, but could be any other kind of information coming in that needs to be computed on the local processing elements. The local processing elements have access to different supply rails, and they can basically say, okay, and the supply rails are kind of correlated to the processing speed. So higher supply voltage means the processor or whatever your element runs faster. So there's a lot of load coming in, for example, and the process itself, all these elements, they decide, okay, now I need to work at the higher voltage and at the higher frequency to still stick within that real-time constraint, because that's also a thing in Spinnaker. You don't have kind of global, so it's all running asynchronously. You don't have time interlocking as in a regular machine. The way you get by that is you have kind of a global cost time scale. So time models itself, all of those, the whole machine is built to push forward whatever problem, AI problem, numerical problem, in real time. And the time steps there are millisecond. So basically processor says, okay, inside the next millisecond, to stick within that millisecond and not kind of take longer with my processing, I need that clock frequency and I need that supply voltage because there's a lot of spikes coming in. Or in the next phase, okay, I don't need it anymore, right? I can even go down to power shuttle, for example. And that saves you a lot of energy, essentially. Okay, so then a lot of memory sharing going on. Then it's a hybrid machine, so we put in MAC arrays as well. So it's somewhere in the middle between a GPU and a more kind of neuromorphic system. Then we put in what we call the neuromorphic accelerator. So that's essentially the math you usually get in differential equations or in Lorentz again. So that's the X block, random generators, etc. Which is actually quite interesting from a circuit perspective. The random generators, they're driven off the thermal noise of our clock generators. Because we're clocking each of those cores individually, we also need to have individual clock generators, right? So each of them basically chooses its own clock frequency, right, to save energy. But that also means we've got plenty of clock generators, right, 152 per chip. And they have thermal noise. So we're just directly using the thermal noise and basically get zero overhead, very high fidelity random noise, 300 megahertz, 16-bit. So we can also do a lot of probabilistic computing in the machine. Then there is the network on and off chip, and that's basically event-based. So in essence, you hit some threshold, right? In a neuron or in a machine learning network or some numerical problem, which says, okay, I now have reached some significant decision. I need to update the other cores, and then I should have packets. And those packets are small. They are built basically for, again, asynchronous sparse communication into the other nodes. So that's also quite different to a supercomputer. Also, of course, the level of processing going on here. So usually supercomputers don't do 10 million parallel, right? We can only do this by going brain inspiration again at the algorithm level. But the individual processes, they're basically microcontrollers. So they also definitely not as heavy duty as your regular supercomputing processes, right? So we need to chunk this into very small kind of elementary operations when we really want to use the whole machine. So really think about it as an M4F is a glorified microcontroller in essence, right? No one could pull a supercomputer out of microcontrollers, apart from us. And there is adaptive body biasing, which is a specific feature of 22 FDSOI of this technology. You've got a backgate, basically gate going into the transistor from the backside, which lets you adjust by adjusting the voltage on the backgate, lets you adjust the voltage variations due to manufacturing, due to temperature, due to aging, that the transistor sees from the front side. So usually you've got a huge spread of those, right? Big sigma distribution, and then you have to choose your VDD, your supply voltage, far outside that sigma distribution. So you have to overdo it basically, because you want each one of those transistors to be fast enough so that you have a timing clean system basically here. And we don't need to do that because the adaptive body biasing, we basically get the sigma distribution way down, which also actually lets us decrease the leakage current. So for example, so H100 board NVIDIA takes about the same all-out power as a Spinnaker board, so 400 watts. But the difference is one of our boards on standby takes 2-3 watts, and NVIDIA board takes 150 watts. Because they basically need, they're a FinFET technology which doesn't have this feature. So in essence, they need to design the system very fast so that it can work efficiently all out, but it's very bad at powering down, right? So it's very bad at doing this kind of sparse processing, which actually machine learning is developing into. So the GPUs are inherently built for dense operations where every element and every single time step basically does the same. They're not very good at exploiting sparsity, which is good, of course, if you do graphics processing, what they originally built for, but it's bad for machine learning because a machine learning network is always heterogeneous. You've got ReLUs in there. A ReLU already gives you basically a kind of threshold that says, okay, so I need to transmit something or I don't need to transmit something at that particular point in time. By the way, I'm almost forgetting. So everyone talking about Mayr here, what model? Right. So one other thing you can be seeing here is that compared to GPU board, we're already going even at the board level, way more parallel, right? On a GPU board, basically you have one big compute engine and a high bandwidth memory stacked on top, and then of course, kind of surrounding DCs and whatnot around it. Here, our compute is already 48 parallel. And again, with local memory. So first you have the memory architecture on the chip itself, the SRAM, but even the big memory basically is distributed. And that's interesting. If we map, for example, standard transformer architecture on here, you can map it in a way that even at that level, right? You don't need to go down to the synapse level, but even at that level, you can basically map it in a way that the local processing only ever uses 99% of the time. There is some long distance stuff, but most of the time you're using the local memory, which basically gives you 4 times the throughput than an A100 board on regular transformers, right? Nothing crazy neuromorphic about it, just because of this brain principle of basically localizing, processing, and memory at this very far scale already, right? That gives basically you don't need to run everything through one high bandwidth memory interface. You get all these LPDDR4 interfaces in place basically. Okay, I'll pass it around. Don't worry, this was one of the initial boards that was tested to structure, so you can have Okay, then we build up a big machine. So again, for the chip, it's 152, 153 ARM cores, 152 that actually we're processing, the rest, the other one is management core. Somehow we have constant size of 100 persons now involved in this. In the beginning, it was 100 persons in the hardware design, so that was essentially almost all my share, plus a lot from our startups that we subcontracted, plus some guys in Silicon Valley that we subcontracted for the memory interface. So that was quite a bit of a management shop there. Okay, Max, you can sympathize probably. Right. Originally, out of the new flagship human brain project, the only thing actually, yes, I have to mention it here. In the middle of the human brain project, when they basically ousted Henry and then Karl-Heinz died, the computational neuroscientists took over, and they basically I got cut down from 7 positions to half position. So it was really just a flying blood, fig leaf kind of thing that they kept us in because they could still claim they're somehow involved. But they basically also told us we already have a Spinnaker 1. We don't need a Spinnaker 2 in the human brain project. And the guru reviewers essentially told me, why are you building Spinnaker 2 out of CMOS? Why are you building out of membristors? So you guys have created quite a lot of membristors. Right. And it has been, again, German Materialstadt, right? So there's quite a lot of money that went into building this machine and deployment, of course, and now the software stack. And the 100-person team has been kind of constantly increasing. It's not just switching over to the software side. So across my chair and spin cloud systems, there's easily 100 persons just doing software stack and application development on the machine. Physically, the full machine will be 70,000 chips. What we have at the moment is the half the machine, 35,000 chips, and 8 racks, so 16 racks ultimately, which we're going to build across the next 2 years. So that's already in the plan. Largest real-time AI platform worldwide, so that's 10 to the 14 parameters we can support. Actually, a bit more. So later this summer, we're pretty close to doing 50 billion neuron real-time simulation on the machine. So that is actually it's a factor 100 larger than anything that Intel's we can do at the moment. We actually have a Nature paper together with them, where after lots of negotiation, they allowed us to come out on top in the graph, basically. But that took some negotiation. Right, it's a hybrid design. As I said, machine learning plus neuromorphic, plus of course all these regular ARM cores that you can use just for a very small chunks of supercomputing, essentially regular computing. So one thing you could be doing is, for example, a mixture of deep neural networks, spiking neural networks, and symbolic AI. So all these accelerators, they actually have their own direct memory access, they have their own state machines. So they are what's called loosely coupled, right? So the ARM core doesn't need to micromanage either the machine learning, the back array, or this neuromorphic accelerators. So you can really run entire networks of spiking networks, entire layers of machine learning networks, and then do still some symbolic Python, C++ based layer on top of that in the ARM cores, for example. So for instance, with KTH.com, we've mapped a language model that has a symbolic layer. It's called NARS on top of the transformer, which which basically pushes up effect accuracy, I think, from 35% to 80%. So it's basically the symbolic layer watching the transformer and telling it, no, you're doing something wrong there. So it's a little bit like the brain, right? These higher layers, MT cortex, they really don't do transformer style. It's more symbolic, like processing that happens at that level. Right, of course, on the right benchmarks, we look pretty good compared to the rest, but don't take from here, I've got a whole slide on then actually the real hard numbers on that. And we very much build for this, again, dynamic sparse asynchronous processing, of course, right? So actually, the regular machine learning is a bad fit to the machine because the regular transformer architecture is full of scheduling. So you need all kinds of operations, software export not happening in precise order, perfectly synchronized across different kind of parallel streams in the machine. So we're working very much on relaxing that, running transformers in an asynchronous way, etc. Yeah, because the machine is just, you can do it. We've proven it actually now in paper under review for the transformer mapping to Spinnaker, but it's not the best way to use the machine. Right, and now let's move on to the use cases. But yeah, that's one digression here. So we're of course not doing just Spinnaker 2. So one thing we're also doing is a lot of edge AI. Mostly, again, not quite neuromorphic, but we figured out Spinnaker is a machine that's good at kind of sparse data in, sparse data out. But your regular sensory data is usually something highly dense, right? Radar data starts are very dense, then of course gets compressed basically to those individual targets. Visual data the same, audio the same. So with our edge designs, we now move towards what we call spin edge. So sparse pre-processing and neural network acceleration for edge applications, which essentially does this dense to sparse transforming. So for those of you who know the dynamic vision sensors, this is kind of similar, but more programmable, more flexible and domain specific. So depending on what data comes in the edge chips, we do region of interest selection, we do delta encoding, we do whatever space-time perceptive fields, etc., or even footnote radar processing, so that what comes then out of the edge nodes is already pre-processed for going into something like Spinnaker at a higher level, so kind of edge to cloud continuum. So that's the general idea with our edge systems. And of course, one particular case of our edge systems is those neural implants, where we do this to quite a high degree, so really compressing the data 10 to the 5 almost compared to the raw data. Right, that's just one indication of a recent chip we did at TSMC 60 nanometer on that. So that's a sparse CNN, and that's the event-based gated recurrent units on there as an accelerator. And that one was actually for smart farming projects, so that's for bigger data, where we're looking at cows and analyzing their behavioral patterns and doing diagnostics, how you need to feed them, how you need to put medicine to them, etc. Right. So I was coming back a little bit to our ecosystem. So that's a timeline of it. So in 2005, we started developing our own chip design flow. So, you know, these multi-billion, I mean, these days you do 100 billion gates on an IC. So you need design flows that encapsulate a lot of kind of inherent knowledge of the designers. Basically what's worked in the past, settings, how you run tools with parameters. So it's a little bit, if you come from machine learning, it's a little bit like hyperparameter optimization. So what happens in a chip design flow with all those different tools you're getting, you basically need to optimize the entire flow, and there's all these parameters going into that flow. So across many years, across many tape outs, you do a kind of very manual hyperparameter optimization, and that then gets encapsulated in design flow. So everybody does it. Infineon does it, Intel does it, and we also started developing our own. A little bit of help there was that, of course, at universities, you get all these nice chip design tools for free. Private industry has to pay a lot for that. So we basically had all of it. We just started playing around. That tool is good for that. That tool is good for that. So we basically could be a lot more freewheeling than compared to private industry in trying on all that stuff. And we usually get cutting edge tools there. Then we started with the serial links. So that was for the wafer, but that was also for some of the software-defined radio chips, processor chips we did with Gerhard's chair, Gerhard Feldweis. 2009, AIC got founded, so they are now by themselves, they're 150 people. Then we start cooperating on multiple systems on chip. Then AIC actually commercializes the design flow on the whole platform, so that AIC is now using AWS, Amazon Web, and having this whole kind of design flow installed. Because these days, in an academic chair, if you want to do design in those, then you have to do that all by yourself, right? You have to develop design flow, you have to install those tools, even just the admin team, because those tools are even that complicated in installing. You need 2-3 persons just basically running your software stack. So that's, of course, prohibitive for small academic chairs. So that's one reason why AIC did it. For other startups, but also for academia, you can then access basically this flow, and you don't need to develop it all yourself. So there's a lot of knowledge already encapsulated there. We get the standard cells, you get the O cells and whatnot. We've actually started pushing out a lot of our engineering also to AIC and similar companies. So I don't need to burn my PhDs just doing the engineering for the chip, so that we can really focus on the stuff, on the core parts that really then make our scientific content, of course, provide the high throughput and the machine and whatnot. Kohlberg got founded in 2013, so that's where we learned a lot about rack level, thermal design, and whatnot. So that helped a lot with scaling up Spinnaker. 2019, Silicon Valley got founded for the communication links. So we're mostly doing automotive communication these days. And actually just made an exit to Microchip. Right, then as I said, at some point, so we started developing Spinnaker in 2013, right? That was the start of the membrane project. 2015, we had the first prototype that was still in 28 nanometer bulk. And then the body biasing, and this whole 22 FTX technology came online in Dresden. And then we took, at the time, a quite risky decision. Yes, we're gonna move the workflow to this Android technology because it just looks too promising. Right, and we had world record energy efficiencies for various microcontrollers, AIC and the chair together. So we really saw there is something there. And then in 2021, we found Spinitron Systems, which was actually a story in and of itself. We knew we had to have some entity because Steve Ferber, who did Spinnaker 1 in Manchester, and then of course we teamed up with Spinnaker 2. There was so much interest from the Neuromorphic crowd that he started loaning out boards. And that was one heck of an administrative overhead. And I knew I couldn't do that at TU Dresden. They didn't like that. The university is not a provider of hardware, basically. So we knew we needed a legal entity to push that hardware out to that crowd. And then we said, okay, if we're doing that anyways, we might as well look at really commercializing it and not just pushing it out to academia. And at that point, we were still undecided if it would rather be kind of a Spinnaker-based edge node or if we're going for commercializing the large use case. At that point, we were still very much influenced by the great project and said, okay, big machine is only good for brain simulation. What's the point? So is there actually something commercializable? And that was interesting because then we started designing the big machine. And through a service company we had there, it's Cloud IT in Dresden, they had some connection to Neon, to that smart city. And then we started networking with the Neon guys, and they didn't have a system that could run this smart city at real time. Because most AI at cloud scale gets quite, okay, these days, with the token optimization, it's actually fast again. But back then, when we first started talking, at Cloud Center, you couldn't get real-time response. And that machine, of course, Spinnaker had this millisecond built in. So you could basically plug in a humanoid robot or a bunch of humanoid robots at one end, do the processing, and be sure to get a reaction inside a millisecond at the other end of the machine. So that's when we first started realizing there might actually be something commercial to the big machine, not just to the single chips. So that's what ultimately they were focused on in the in spatial systems. And the reason I call it a biotope is basically because with a lot of those companies, we're still very close. We do lots of projects together with them, which basically means, and of course, virtually everyone at my chair has some kind of secondary job at one of the startups. So that means it's a huge ecosystem of both people that basically know each other, that work as a team, that have designed IP components together, where everything fits like a glove to each other. So essentially, when I do a big machine like Spinnaker, I just know across this whole ecosystem. There's the communication links. There is the ultra efficient processor design, blah, 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 blah. And essentially, okay, it's not quite as simple as that, but essentially you should plug it together, right? So this is not a job you want to be doing with a chair of fresh PhDs, essentially, right? So you want this kind of ecosystem, 200 plus tables behind it. This is a small timeline of split cloud systems, right? So 21, we incorporated it, then 6 employees, 15 employees, 27, 67. Actually, yeah, the Series A is pretty much closed now. Took longer than expected, but anyways, you know about that. So the hiring target until, so right now it's about 80 people in split cloud systems, and the hiring target for end of this year is 140. So we're gonna hire basically another 60, 70 persons until end of the year in split cloud. Which basically, of course, means you get thousands of CVs, right? Because you want to vet those guys. You're not just hiring the first 60 that come in. Right, subsidiary office. And actually, this is a quite neat instrument on the EU level, the AIC grants, this Transition Accelerator grant. So there really, I think the EU has done something right. It's quite a stamp of approval, basically, also with investors that like that. Okay, so to sum up Spinnaker again, and then we move on into the applications. Always think of it kind of 3 words combined. So it's AI or DNN processing, almost like in a GPU. You get the flexibility, like in a regular supercomputer with all those CPUs, and you get probabilistic computing, almost like quantum computing. We actually do quantum computing emulation for IQM these days. So it's if a problem fits to that, right? I'm not saying Spinnaker 2 is a half or a be all. Compute, anyways, is getting almost fractured, way more heterogeneous, right? You've got accelerators for this, for A, B, Z. But if the problem fits to that, I've identified quite a number of cool problems that need this kind of combination. And then you really see the KPIs. Then you're really a lot faster than any of the competing hardware, basically. Then you get all these brain-like efficiency features, right? The sparsity support, this ultra-fast asynchronous parallel operation. And we usually see between 1 and 2 orders of magnitude speed and energy advantage on regular compute problems. There is some problems, like I'm going to show you the finite element methods, but we actually see 3 orders of magnitude. So for the finite element methods, at the moment we see in factor 8, 900 compared to GPUs faster. So again, it's a game changer for stuff that really fits to the machine. Not your regular AI jobs, but hybrid jobs, yes. So let's go into the use cases. So one very simple one, just to drive the point home. This is hooking up a vision sensor, dynamic vision sensor, to 4 cores of a Spinnaker 2 chip. So dynamic vision sensor essentially does a delta coding. So you can see the hand moving there, and you see basically pixels. So what's great is pixels not reactive. So you're reducing data rate by essentially negating anything that's not moving. You just see that hand moving. And you see that the black and white basically is upwards or down. So increase in contrast or decrease in contrast essentially in the delta encoding. So you can basically also do movement detection and movement direction out of these elements. Let me rewrite it. So what we've done is we put this in 4 quadrants, these 128 and 128 pixels. And there's like 2 levels of savings that you can do on the machine. One is, of course, then just this delta encoding of the sensor. So this blue is the power levels, red is the computation time. So you can see essentially that the power levels are shuffling around, right? That's what I said. According to how much data is coming into the machine, into that particular code, the code will decide, do I now need to process all out because I need to stick within that millisecond real-time time scale to process away the events, or can I go at a lower power level? So that's the first level. The other level is, this is very simple hand tracking center of mass algorithm running there. It's like a attention mechanism. Then only that core gets activated where that hand tracking is, right? So that's the second level. The other ones are completely in power shut off. Let me rerun it again so you can see it. So in this case, right, it's only that core active for 0. So the other ones, you can see they're completely in power shut off. And that core then again manages its power level, so its clock frequency and the voltage the process runs it in accordance to what's coming in from the sensor. Then the red dot moves over there, right, with the hand. Then core 1 is active, core 3 is active, core 2 is active. So if your data comes in like that into the machine, or you find some clever way inside your algorithm to encode data like that, we also have these algorithms, then essentially you get 2 things. You first get a lot of energy savings, but you get a high throughput as well, because you are using your compute more efficiently. If you have focused information representation like that, then, I mean, you can cheat physics, right? GPU board, our board, you get so and so much compute essentially, right? So, let's say activation function times synapse per area and per unit of time. But if you then always assume there is dense processing, for example, going on across an entire sensor, then you're doing a lot of rubbish computation. You're doing 0 times 0 computation, right? If you compress that and basically threshold data like this, then you're using available compute more efficiently, actually getting more throughput per time. So essentially, if machine learning, more tokens per second. So that's a very simple example there. Actually, how am I doing with time? Let's move up a bit. Transformers. So usual transformers, ChatGPT, whatever. Knowledge is very distributed, right? So any prompt, even very trivial prompts coming in, you need to activate at least 30–40% of the entire transformer, which means pulling those bits from memory, doing computation on them, communicating them from A to B, which all takes energy, which all takes time, right? The interesting thing is, if you look to biology, all of you, there's nature papers on this, actually we do Skywalker neurons in your brain. So this is neurons that are very, very selective. As I said, neurons are very good at powering down, and they're very good at basically just activating when they're needed. And this neuron in particular is 10 to the minus 5 silent. It virtually only ever activates if Mark Hamill is basically on screen, Luke Skywalker written, Luke Skywalker spoken, right? That's how selective that neuron is. So that would be cool, right? If we could do a transformer like that, and we don't need to activate for it. Basically, we put a prompt to the machine, who's Luke Skywalker, and we need to activate only a single neuron with all the information. That would be the ultimate goal. So the thing is, sounds like science fiction, actually not. Google DeepMind, Meta, they're all now doing models. They go in that direction. They call it the fast feed forward, they call it the peer layer, they call it the middle mixture of experts, but it's all the same principle, which basically means you have a prompt coming in, and you've got a fast log scale, typically algorithm that looks at that prompt and then down selects, even down to the single neuron level. It's a very fine grain which of those neurons in the transformer do actually need to activate to answer that prompt. And what we've teamed up specifically with Google DeepMind, with OLE there, and what he's showing is a factor 1000. So not quite the 10 to the 5 that the brain can do, but still going a long way in that direction. On average, in 1,000th the resource, not 30%, right? Not 10%, not 1%. 0.1% of the resource of a network to answer that prompt. The thing is, he then mapped it to TPUs, to CPUs, to GPUs, and only ever saw factor 10 out of this factor 1000. So now we actually First we teamed up with him, now we hired the whole team from Google DeepMind, away to spin-cloud systems, and now we're mapping that stuff to Spinnaker, because Spinnaker is about the only hardware that is that fine-grained selectable, right? All the GPUs, they just, even Cerebras or Grok, they all assume this dense processing, which this typically is not, right? It's not a dense processing. So you really need a hardware that's as fine-grained selectable as Spinnaker. So again, not science fiction. This is really happening. And at the moment, we're already seeing a factor 100 out of that factor 1000 for the transformers. So it's really, I think it's a factor 200 on the energy efficiency, the latest figures, and a factor 50 more tokens per second on the same board compared to GP. Right? So that's already kind of distributed. It's very sparse. It's in reduced position. It's not yet asynchronous. So that's what we're currently doing, so that we can also have this ultimately parallelized across many units without all the scheduling, which is actually interesting, especially if you run a transformer in a reasoning loop. The reasoning loop gives you an RNN-like capability. So we've proven theoretically now, but now we're mapping it, that you actually get a kind of attractor-like behavior if you run transformers in a reasoning loop. Which means even if single kind of paths of information across the forward paths of the transformer are asynchronous to each other, you're basically catching them, integrating them in the reasoning loop again, and you are guaranteed to still arrive at the attractor, basically at the answer to the prompt. So you can really run transformers asynchronously if you run them in a reasoning loop. So that's the latest we're integrating, which especially has sort of the software stack, right? The software stack is, if you want to do this high level of scheduling, it's a nightmare. If you just throw that stuff asynchronously across many cores, you just replicate code basically, makes the software stack, makes all the difficulties in the software stack almost go away. So the guys, especially in the software department, are in spin-cloud systems are very hot on that. The next goal is achieving the same for trading, actually. So right now we're doing this for inference. Which kind of goes along that direction. I won't be spending too much time here, but it's what we call block local learning. Actually, we have a workshop on that next week at Wolfgangsee in Austria, where we're advancing this stuff here. So yeah, again, won't bore you too much with that. We started out with an autoencoder. That's the stuff up here, right? So you start with an image, you compress it down to bottleneck layer, and then you try to reconstruct it from the information that makes it across the bottleneck layer. And we're not just reconstructing the image, we are trying to derive a measure of the uncertainty of the individual layers inside that autoencoder. So that's the actual error we're making on the reconstruction. You can see it on the chart. It's basically unsure about the reconstruction of that letters here, right? And the predicted uncertainty correlates very well with that, right? So the network knows where it's uncertain, which is actually not quite a trivial thing, right? It has an error, but it also knows where it can predict where it makes that error. So that's actually old stuff here. And then essentially folded the autoencoder. So now the upper part is the first part of the autoencoder up to the bottleneck layer. Now only the bottleneck layer is basically the class labels. It's the output of the deep neural network. And then the second half of the autoencoder essentially gives us, now we basically just doing the uncertainty here in the second half of the autoencoder, which gives us the local loss going back in here. And people have done this. Geoffrey Hinton has something similar. He calls it forward. So that's kind of local learning rules where you have a local loss just going in a local subnetwork, and you try to just train locally. You don't need global backdrop. You don't need this linking of the class labels all the way into the local network. You just run with the local loss and try to basically get a gradient from there and train the local network. The thing is that if you only go by local loss, you usually only can do something like MNIST, very shallow networks, because you're losing the gradient that's only coming from the ultimate class labels. So what our block local learning does is actually it's a hierarchy. So it's more like you actually have the global losses at the basically the bottleneck layer, which means the class label output, and then you have a gradient. So at the very basically at the individual level here, we are at a complete local level, just doing essentially what biology is doing, feed-forward training based on correlations. And in between, in the hierarchy levels, we're getting closer and closer to standard backdrop actually. So we actually, this is the first local learning rule that can actually do deep neural networks. So we've proven that in a paper at ICLR 1.5 years ago. So we're actually doing same convergence speed as backdrop, same ultimate result as backdrop, but with a factor 10 less communication overhead. And actually even reduced precision, because we're mostly working off the local loss, mostly, not all of it. We don't need this floating point performance that we usually need for backprop, that represent floating point for all these new formats. You can actually get by with fixed point precision most of the time, because you're only ever trying to hit the local gradient, basically. So so essentially what we have at the moment, this is distributed learning. This is not yet asynchronous. So we work on asynchronous learning as well, we've got some good results on that. Basically, and sparsity is also not in there, so we're working on that. So at the moment, again, across the scalable principle of the brain, distribution, sparsity, asynchronity, we've got building blocks that learn each of those, so that are optimized in learning, in training for each of those. This summer, we are really trying to, in this workshop, to get all of that together, so that we then really have a training algorithms that is on par with backprop in terms of performance, but that basically does asynchronous, does distributed, does hierarchical learning, and sparse. So these kind of 3-4 principles. And our projections say we could get ultimately we could get the training effort down by 3 to 4 orders of magnitude compared to backprop if we integrate all of that in one algorithm. So right now we only got bits and pieces of that. Okay, very last one of the use cases. So this is completely taking a different track. Now, what I showed you right now is mostly along this AI-neuromorphic, right? So trying to do image reasoning or whatnot. This is something, again, completely different. This is mostly from the Sandia guys and a couple of other groups in the US that have started working on Spinnaker. They had this crazy idea of mapping numerical algorithms to a spiking network. And I always thought, this is just computation, neuroscience, whatnot. You can't really use that. It's playing around academically. But they had some very cool projections how that would scale. And they just didn't have the hardware. Not even Loic was scaling to that level. Now, basically, Spinnaker is scaling to that level. Essentially, running numerical algorithms, like quadratic unconstrained binary optimization, like a finite element method, in a spiking network. Because what does a spiking network give you? Again, it gives you asynchronity, it gives you sparsity, and it gives you distribution. So very highly distributed algorithm with very elementary single operations. You don't need big numerics at the single level to simulate the single neurons. So if you map a numerical algorithm to spiking context, you get strong scaling, what the supercomputing people tell you. So essentially, by going asynchronous, you don't have these wait cycles where one part of the machine waits for the other parts. By going sparse, you're not running into bandwidth limitations. So again, you can have a very large machine without flooding bandwidth and slowing your machine down that way, right? And by going distributed, again, co-localized local processing, local memory, which gives you very fast execution essentially, because you don't need that much long distance communication. So that's the cool stuff. And the reason why this works, that's interesting. So you map this whole cubo matrix to a spiking network. So the cubo matrix encodes all these, for example, what we're doing with Infineon now is optimizing manufacturing flow for the wafers. There's hundreds of machines in there with lots of constraints, lots of target conditions, lots of different times that a wafer needs to be added. That machine needs to go out of that machine, etc. So it's one huge problem. So that maps that to a large instance of Spinnaker. And the interesting part is, again, there's basically subparts of the problem that are subparts of the Q matrix. And if one part of the Q matrix kind of finds a local solution there, shoots off stuff to the other parts of the machine with sparse messages. And the whole reason why this, so we need to still arrive at a global solution, right? We need to not just have these local solutions, it needs to be a coherent global solution. And at first I thought this was actually an approximation, but the simulations we did on, or the runtimes we did on Spinnaker with MagCut problems, for example, standard benchmark, we actually at the state of the art in terms of the number of cuts we find in the graph, for example. And the whole reason is because we've got this global real-time timescale. So because this Q matrix is pushing across the entire machine forward at the same time scale, then if that subpart of the problem is found, gets communicated over here, then that part of the optimization process can integrate it because it is still coherent, because that subpart of the matrix is at the same point in time in its solution. We actually did simulations on it, so we could push this off by about 100 milliseconds relative to each other. Then you would lose the coherence. Then it wouldn't be an optimal overall solution anymore. But that is quite a high level of asynchronity, right? So up to 100 milliseconds plus minus, basically, this problem still stays coherent, despite the processes being running completely asynchronously relative to each other. This is another example. That's a finite element method I was already hinting at. So again, finite elements mapped to a spike in context. And this is actually stuff from a Louis paper. I can't show you the numbers from Spinnaker because, again, big reveal, big code bell submission on that coming up. So can't pre-show it here. But anyways, the main point being that you can see the speed up here. So the speed up is ideal. You basically, apart from that, of course, it runs into really size problems when it dies off. But for the first part of the curve, you see ideal strong scaling. Basically, forget Amdahl's limit. You throw double the number of cores at the problem, you really get a speed up of that factor, basically, right? Of a factor 2. Or to put it another way, if you have a graph, let's say size of the problem versus compute time, then on a regular supercomputing machine, you're going up linear, going super linear, right? The bigger the problem, the longer it takes an execution on that machine. On Spinnaker, it basically flatlines because we have the same time to solution because of the shear time scale up to the full 10 million cores. So up to the 10 million cores, basically taking the same time to execute the problem, irrespective of problem size. So what we see right now, I think I've got this coming up. Actually, let's go here. So what we see right now is a factor 800 fast execution on a Spinnaker board compared to a GPU board. And this is just for single board, right? And with us flatlining versus the GPUs going up like that, the larger problems we map on the machine, this gap will get actually wider. So this is really at the small scale, we expect 4 to 5 orders of magnitude than for the bigger scales. And just a small outlook. Essentially, what this is one problem, drug discovery, it fits very well to Spinnaker. Actually, to the point where we now have a dedicated Spinnaker machine in Leipzig, just for drug discovery, because it is a hybrid problem. So parts of that is generative AI, molecule design. Parts of it is Monte Carlo type stuff, for example, for electron density estimation. And Monte Carlo is also one of those algorithms that shows strong scaling on Spinnaker. We also do that in a spiking version of Monte Carlo. You need finite element methods for physical emulation after you have the electron density. And you need probabilistic computing. Actually, the other one is up here. It's not quite hierarchically. After you have the initial molecule design, you've got van der Waals process that basically still fine twist the molecule. And with Vanderbilt University, we now have a cubo formulation of that. So you essentially do an optimization problem where the molecule moves around in its cubo space and basically finds its final folding shape, which is then, of course, the shape that makes it medically active. So they want to get it with high accuracy. So we're actually using probabilistic computing, this cubo computing, to refine the initial guess of the generative network. So basically starting with the AlphaFold, then going even higher precision with a physical method. And then even for the electron density, we're starting again. So after that step, we're starting again with a generative approach. So you can do a nice electron density distribution with transformer network. But then you also need to refine that with a numerical method again. So this is why I'm saying this problem fits well to Spinnaker, because it really uses these kind of triple hybrid aspects of the machine. Okay, so here's a rundown where we are with Spinnaker, or most boards, yes. So we basically had, especially now with Spinnaker 3 work going on, we won the first and second round of the Spontaneous Compute Challenge. We had this transitional accelerator grants. We had this, this is not directly connected to Spinnaker, that's more the edge AI. We had this 1 million EMF award for an energy efficient edge AI system. Then, of course, these days are almost more prominent in Europe's ICML and ICLR than in ISSC. So doing more algorithm work almost than circuit design. But it's interesting because the machine learning people really have started noticing. Usually they will dismiss it. Are you neuromorphic guys with those 100 parameters? We don't take it seriously. But if you really do these gradients by neuromorphic principle at that scale, they're starting to notice because it actually helps them in their algorithms. Like this team up we now have Google DeepMind. Very recently, of course, a month ago, we got the Mayr leaderboard. So that's the main award of the neuromorphic community for the whole Spinnaker ecosystem, across Spinnaker 1, Spinnaker 2, and all the commercialization. And of course, guys in Zambia, etc., they're getting all systems. Actually, we took over from Intel there. So A lot of people were dissatisfied with the Intel solution, and now they're purchasing Spinnaker. We actually featured on the Department of Energy homepage as kind of next generation AI test beds. So it's also not quite bad. And again, we're outdoing Intel and some other competition by at least a factor of 100. And this is the machine for drug discovery in the background in Leipzig. And this is Jens Mayr, so he's my main collaborator in Leipzig and one I did on the drug discovery stuff. Okay, so here's the hard, really non-fake, wall plug power, tokens per second, whatever, hard numbers. So drug discovery with 50 times more energy efficient, 10 times faster GPUs. There's just a paper accepted on that. DNA training at the moment, 12x more energy efficient. Again, we're just trying to get those methods together. And we're really seeing several orders of magnitude, and not just energy efficiency, also speed. Finite element methods, factor 800, I told you, optimization about a factor 60. So we always compare either to GPUs or CPUs. You can see that Spinnaker is somewhere in between, but we took the state of the art, right? If the state of the art is CPUs, we compare to CPUs, otherwise we compare to the GPUs. That's where we're coming from with the smart city stuff, right? So there, of course, throughput is a thing, and of course the energy efficiency as well, and this Azure cloud continuum. Again, these are the old numbers. This is really just the effect you're getting from what I told you, this co-location of a standard transformer. That already gives you this 3x more tokens and a factor 20 about energy efficiency. But right now, of course, we outdid those numbers with those kind of millimeters of expert transformers. So right now, I told you the numbers are more like 200 here and 50 here. Right, that's the current users. Again, so spread out across private industry, academia. So Spinnaker 1 had 150 use groups around the planet. Steve was always joking that the only continent that didn't have a Spinnaker 2 board is Antarctica. So probably going the same route as Spinnaker, of course, the Spinnaker 2. We actually also use it in teaching. So we use it in our master for applied AI entries and in the master in our electronic systems. And the guys in Heilbronn, the Schwarz campus, they're also purchasing Spinnaker for use in their teaching. And very last outlook, so we're already going, of course, towards Spinnaker 3, because there's actually another reason why I founded Spin Cloud Systems. Steve, back then, he got totally sidetracked with the use cases and supporting Spinnaker 1, so he never did a single chip afterwards. He got totally sidetracked with user support and engineering. So I wanted to push out a lot of that software stack development towards startup, right? That then we could build the real cutting edge use cases, proof of concept on top of that software stack. And then, of course, if that pans out kind of commercially, then we would push it over into Spin Cloud again. So again, the reason I'm saying this is because I wanted us, our DNA is chip design, right? I didn't want us to get sidetracked just to support and software. Of course, we're doing a lot of that these days, but we're continuing with the edge nodes. And since 1.5 years, we've got the first 2 grants going into the Spinnaker 3 design. So right now, actually this number is old. It's more like 10 million now that we've got secured for the initial Spinnaker 3 work. And that's going to increase, of course, to the same order of magnitude. So 30, 40 million, ideally, if I'm successful, before we've got the next kind of system. So the timeline there is 8 years, basically. So a 3-year phase now, where we do where we try on all kinds of new circuit components, then a 3-year phase where we design the final chip, and then a 2-year deployment phase until we've got the big machine again. So the thing is, we go way more event-based on the whole architecture. So basically, the Spinnaker 2 design was spread out across Manchester and Dresden. Manchester more on the system level, me more on the chip level, because that's in our DNA. But that ultimately, because also kind of 80–90% of the effort was on the Dresden side, that led to the machine kind of being developed from a chip perspective. Also because Steve didn't really have use cases for the big machine. He got sidetracked by these single board use cases. So we didn't have a lot of guidance, actually, how Spinnaker is good or bad in its features at the cloud scale. So that's why I'm also focusing a lot on this cloud scale to really get use experience there. So basically, we're going to have, we're actually building that up right now, simulation model of Spinnaker 3 from the get-go. So we can do virtual mappings of algorithms on the machine, see at the machine level, what kind of accelerator design, what kind of communication architecture is good, basically, for those types of algorithms. So it will be a lot more a holistic system design. fully event-based throughout the architecture, of course, scaling to smaller technology, blowing up the pure number scale will be the same as between Spinnaker 1 and Spinnaker 2. That was about a factor of 50. So we compressed one of the old 48 notebooks inside a single chip in the new system. And of course, now we're compressing again one of those big boards into a single chip then on Spinnaker 3. We're actually going to use non-volatile memory. So we've got a project with a ferroelectric memory company on that. We're going to use their fake caps very likely because we need a memory stack that's good at going into power down. So basically, if you've got non-volatile memory that is as dense as DRAM, that's of course total, godsend for all type of algorithms. Yeah. Of course, everybody labels things AGI these days, right? So we needed to do that for the politicians, but it will be basically a machine that's really then at the AGI scale at least. Of course, we still need to develop a lot of algorithms on top of that. At the AGI scale, but doesn't need these 100,000 GPU data centers that you need these days, right? We want the training more efficient, we want the inference more efficient, so that we also have kind of AGI, or whatever you want to call it, at way closer to a human scale, so way closer to those 20 watts we've got in the brain here. Probably won't hit it, but you definitely won't need a nuclear power plant next to this machine then. So that's the general aim there. And this is the teams, right? So this is Manchester, and now John, Davide, and Andre have taken up the mantle from Steve. This is my chair in the upper right, and this is Spintown Systems again. These days there are 80 people, so that's you can't make pictures fast enough to make the team grows. I would need to take a picture every month. And this is a lot of our albums. So this is Anand Subramani in London. This is our couple in Bielefeld. So they are ex-Graz people out of Wolfgang Maas's lab, for those people who know it. And these are my two main algorithm collaborators, just building up the groups in London and Bielefeld. And again, I'm going to meet up with them next week in Wolfgang's sale. And we're going to talk about the next level of the training algorithms quite a lot. Right. Now, feel free to jump across it. That's a good one to find event. And by the way, I still have one nugget, and this is the first time actually also people are seeing this. So that happened 1.5 months ago. We're still getting the video together. Sanya has been pushing us because they wanted this finite element methods to scale up. And they only have kind of 2 frames at their place, so they need the big machine in Dresden. So then we obliged and did the wiring up of the big machine. So what you're seeing there, the white stuff, that's just the host communication, the video with Ethernet, but the boards were individually at that level up till 1.5 months ago. And then all these multi-core cables that are in these orange sleeves basically hooked them up across end of April, beginning of May. So that's the motion capture video of that. You can see how it's growing by the orange cables. So again, not vaporware, this machine is there. And it actually looks quite messy, so we need to figure out some way to make this a bit better. There were customers like Risha at UTSA, she basically said, don't you have some way to make it look nicer? This looks way too experimental still.
Needed a team of good German electricians.
Yes. Right. So there was a wiring competition. Thank you.
So yeah, thank you. Wow, incredible engineering feat, I would say. Even an applause for it.